Um,
Welcome.
thanks for joining us today in this webinar. It's my first one, so hopefully you'll bear with me and overlook some of the mistakes I'm probably going to make. Looking back over my career in this industry, I remember the first day I applied for a job at Anaconda. They were looking for a team of 6 people to start up their fiber optic cable program. I went in and introduced myself, gave him some of my background, and talked to the boss. And I said, well, what's this all about? And he said, well, we're going to develop some cables to protect optical fiber for use in the industry. And I said, well, what do you do with that? And he said, well, that's what they're going to use in the future for telecommunications. And use, instead of electrical signals, they're going to use light signals. I go, wow, that's pretty cool. I said, well, I'll give it a shot. I mean, I'm unemployed at this point, so why not? And that was 40 years ago. So it's been a great ride, I'll tell you. Okay. What is fiber optics? What is it? Well, simply put, fiber optics is the transmission of light pulses over an optical fiber. It has to obey certain laws and rules in order to get to the other end. But if you look at this slide here, you'll see that we have 2 modes of light propagating down the fiber. And it also shows you at the beginning, or at the source, where you're going to have 2 angles shown in the both of those angles are what we call critical angle. And what we're saying is that any light ray that propagates into the fiber that's greater than the critical angle will stay within the fiber and bounce its way on down till the end. Any light ray that is less than the critical angle will more than likely get refracted out and lost. The one thing I will want to add here about fiber is its ultra purity. They use a fused silica material and then add some dopants to it when it's being processed or manufactured. And the fiber itself is so clear that if the ocean was made out of it, you could see to the bottom of the deepest part of the ocean. And although that's pretty darn clear, it still has some issues, as you'll see, propagating light down its length. In total, the concept of fiber optics is called total internal reflection. The light rays have to meet this requirement to make it down the entire length. And you can see that in light. We're going to be talking about index of refraction, reflection, and we're going to show you how to calculate that or some of the math involved. But if you look at the green turtle here, you'll see that you have light coming from an outside source, in this case the sun. It's going through the air, which is one of the fastest mediums that light can travel in, besides a vacuum. And it's refracting through the water, which is a denser material, and bending. And you also get some reflection off of the turtle to your eye. In the second slide, or second photo, you'll see total internal reflection as it relates to a light ray going down an acrylic rod. You can see the angle of that ray and that it continues to reflect back into the core all the way down the fiber. And that's what we're going to be discussing today, is how do we make that happen? How does that work? Why do we use it? Well, it seems pretty obvious, but from looking at this slide, You know, one of the big problems early on with optical fiber was you know, the desire or the insatiable desire for bandwidth or information carrying capacity has been with us for quite a while. And of course, you know, the internet ratcheted that up a tenfold or whatever. So what we had going into this technology is we had a bunch of 600 pair telecom cables, you know, twisted copper pairs in a lot of ducts in cities that were filling up those ducts. So they couldn't really expand their capacity without digging up all that all those ducts and putting in new ones. Or when this came along, they figured out that they could pull those out, those big cables out, put in a few inner ducts, and you could actually put one cable in one of those inner ducts and equal the same amount of carrying capacity or bandwidth capacity as you would the 600 pair copper cable. Well, we've updated this slide by showing you it's the same philosophy with the Cat6 cable. You can see that the fiber optic cable right there is going to give you as much capacity as the Cat6 cables, but it's going to take up a lot of space in outside plant, in the ducts, in burying the cable, et cetera, et cetera. And why do we use fiber? Well, as you can see from the first slide, you know, it's going to take up a lot less space to give you the same capacity or the same bandwidth. But what we can also do is we can go a lot farther without having a repeater. You can see here some of the examples from the Cat3 all the way up to single mode. Each one of them being advanced or have increased carrying capacity. You can see single mode here shows that we're doing 90 kilometers up to about 1 gigabits. Well, of course, nowadays we're looking at much greater bandwidth than this, or capacity than this. We're looking at 2.5 gigabits, 10 gigabits, 100 gigabits over systems, which is incredible to me that you could turn a laser on and off that quickly, and the fiber down the fiber, and then the detector on the other end can make sense of it. It's an incredible technology. But the Cat6 has an effective range of about 300 meters. So even though it has good bandwidth or good carrying capacity, it can't meet the upside ability of the optical fibers, and it can't go the distances that they can go. You can also see here multi-mode fibers, and those are fine for limited distances and limited bit rates. They're much easier to handle. They're less expensive. They're much easier to splice. So they definitely have a place in our industry. Why do we use it? Another reason is their immunity to EMI and RFI. In other words, they're not bothered by noise on the line. And of course, this is great for the utility industry because we put these fibers right up in the electrical fields. And if it was a copper cable, we'd have all kinds of problems. It's also less likely to be tapped. When it is tapped, you can see that in the control room that you've been a break or a loss in the system. You'd have an attenuation at that point, so they can track that down. The other thing is which we didn't put down here, is it's less costly to deploy. You know, there's going to be less cables, less repeaters, less of all the things that you would normally do for cables or copper cables. How does it work? Well, this is a pretty cool slide here. This kind of shows you what internal reflection is all about and some of the other terms that we're going to be discussing. We see the acceptance cone on the end of the fiber, and what this is telling us is within this axis, within these angles of refraction, all the light that enters into that acceptance cone will be propagated down the length of the fiber. If it's outside that acceptance cone, it'll be refracted into the cladding and lost. You can see here that, well, I guess we're going to get into that in the next slide, but you can see how we define these angles. We get into Snell's law, but that's a function of the index of refraction of the core and the cladding. And again, I'll get that in a minute. Okay, we're going to get to the physics behind it. Mike must have slipped this one in. I don't remember that one. But anyway, we got to see a side view and a cross-sectional view of an optical fiber. And you can see here that N2 is the sign for the cladding and N1 is the core. The core is made out of a glass that's a denser material than the cladding. And this has to be this way in order for the ray to propagate down the fiber. And the way we calculate index of refraction is that it is the speed of light in a vacuum over the speed of light in the medium. And in this case, in most optical fibers, the core has a index of refraction of around 1.5, which means that these light pulses have slowed way down to about 200 million meters per second. So it's really slowed up. Snell's law, and a slide showing what we've been talking about as far as index of refraction and total internal reflection. In 1621, a Dutch astronomer and mathematician created a formula, or come up with a formula which shows the relationship of refracted light through two mediums with different indexes of refraction. In other words, two going from a dense to a less dense, or a less dense to a dense material. Now the materials have to be transparent so the light can go through them. But what he's saying is that when you go through the first medium, if it is less dense than the outer medium, or vice versa, what you're going to see is a slowdown or a speed up of the light pulse. If you can kind of imagine, if you will, take a look at this ray right here. You can kind of imagine this as being a car with four wheels on it. It's going to get to a point, it's going to get to the interface, or this boundary between the two materials, and we'll say that the O2 is mud and the O1 is air. We know that light travels much faster in air than it does with water or mud. So we're going to go down and we're going to drive this car down here, and we're going to hit the first tire that's going to hit the mud is the right front tire, and it's going to start slowing down, okay? And the outer tire is going to continue to move faster. And what's going to happen is that car is going to turn in the direction of the normal line, which is the reference line that Snell uses for all calculations of refracted angles. This light coming in is the ray of incident ray, and theta 1 is the angle of incidence. it is refracted in the material, in this case the core, and it is bent, and that it would be the refractive ray, and theta 2 would be the angle of the refracted ray. Over on the, hope I explained that all right. In the other slide, I think it's easier to show, where you've got in the first illustration will show that the angle of incidence, which is here, is less than the critical angle. Okay, the critical angle is going to be over in here somewhere. Okay, what we're seeing here is that when the angle of incidence is less than the critical angle, it's going to refract into the cladding and be lost. Okay, that's a source of attenuation. In the second slide, or the second photo, you're going to see where the angle of incidence is equal to the critical angle. Okay, now we're going to get our definition of the acceptance cone. Whereas this forms one side of the cone, and then the other side will form the other. And this is a series of angles, these angles of rays that are accepted into the core of the fiber and allowed to propagate down the fiber. So this is what we call the critical angle. In other words, everything that's greater than this angle will be reflected and kept inside the core. Everything that's less than this angle will be refracted and lost. And over here, you're going to see a slide of what we call total internal reflection. Whereas theta 1 and theta 2 are identical in value, identical angles. And if the light ray enters at this angle, it's going to be reflected into the cladding, back into the core, and on its merry way into the end of the fiber. I hope I made that clear. And we talked about this a minute ago, the acceptance angle. The acceptance angle and the numerical aperture are, of course, related, but they really are talking about the light gathering capability of the optical fiber. This is going to tell a source manufacturer that the output of his laser or LED, most of that it can vary through these angles and get light into the optical fiber. And the numerical aperture is roughly the half angle of that. Wait a minute. Okay, I'm sorry. Here we go. It's roughly the half angle. Let's see here. It's the sine of the half angle of the acceptance cone. And if you want to look that up and do the math, go right ahead. I'll be glad for that to happen. Oh, okay, we're getting into stuff that I better understand. These are the basic types of optical fibers that we use every day in our industry. They vary in size, they vary in capabilities, and they're for certain applications in the field. The 62.5 is a relatively new fiber type. It is primarily used for lands, where they don't need huge capacity. It's easier to handle in the field. It takes a wide range of sources, and it takes some mechanical connectors as well. The 5125 fiber is actually the first fiber I ever used in the industry. It came out before the single mode because of the sources that were available. It can be used in a multitude of different applications, and you see bandwidths for the 50 micron core from somewhere around 200 megahertz kilometer down to up to 1500 megahertz kilometers. So it has a wide range of capability. depending on the which fiber you buy and the source that you're using. And the OS2 or OS1, depending on how it's being used, is of course the single mode fiber, which is used for almost all long distance communications at this time. When we talk about light, we're talking about part of the electromagnetic spectrum. The spectrum is just simply an electromagnetic wave that in different frequencies. And for fiber, they've chosen the infrared spectrum to transmit or to use for optical fiber. Now, the reason they did this is because, as we're going to learn a little later, is that this is the area where silica glass has the least amount of attenuation. The properties of an electromagnetic signal. This describes what a wavelength looks like. It's the full cycle of a This is a full cycle of an electromagnetic wave. It's the length of one peak of the wave to the next peak of the wave. Let's see. We measure those wavelengths in nanometers, which is a billionth of a meter. Fiber performance factors. The two key optical performance factors are attenuation and dispersion. I'm sure you've heard this a lot in your career. Attenuation is expressed in decibels lost. It's a result of intrinsic issues within the fiber and extrinsic conditions around the fiber. What it does is it impacts the ability of the receiver to have enough power on the receiving end of the pulse, so we could recognize that as a 1 or 0. A 3 dB loss in power is roughly 50% of the input power. Dispersion is the spreading of the signal pulses. There's 3 types, minimum of 3 types. There's modal dispersion, which is primarily affects multimode fiber, chromatic dispersion, and polarization mode dispersion. Intrinsic attenuation. This is the attenuation that's created during the manufacturing of the optical fiber. You can see that the majority of this attenuation is in the form of scattering, what we call Rayleigh scattering. It's where the light pulse is hitting an impurity in the optical fiber, and it's absorbing that energy in the form of heat, and we're getting losses in the optical fiber. The absorption is really where there's excess amount of hydrogen or hydroxyl ions in the fiber, what we call moisture or water, and those also absorb the light energy as it moves down the optical fiber. One of the benefits of Rayleigh scattering is that we can use, as it hits these, I guess I should go to the next slide. Here we go. Absorption, as I indicated earlier, it's where we're going to hit an impurity. It's going to excite that electron, and then it's going to turn into heat and lose energy. Rayleigh scattering is kind of interesting in the fact that when I hit an impurity, it's going to reflect that light or that ray in all different directions. Some of the rays are going to go forward to the end of the fiber, and those aren't really called losses. Some of them are angles such that it's going to escape the out through the cladding and out of the fiber. And the other ones are going to go backwards towards the source. Now these rays are what we use for the OTDRs. They pick up this backscatter measurement and interpret that energy as giving us length, attenuation at that point, and any kind of discontinuities throughout the fiber. The extrinsic attenuation, these are normally caused by after we get the fiber from the fiber manufacturer and it goes to a cabler or an installer. This is generally what we can do to the fiber to make it more lossy. It's usually created by large bends, and what happens is during these bends is that these fiber angles change. I mean, the ray angles change within the core, and once it gets past, or once it gets less than the critical angle, it is going to go ahead and refract out of the fiber into the cladding and out of the energy field. But we can normally fix this after installation or after cabling, and a lot of times this loss will be reduced. So what we'd like to do is take a look at the values on the reels where there's not bent so tightly, or after installation, and we can see if some of that macro bending didn't go away during our processing. Micro bends are a little bit different. And if you can imagine putting a fiber between two sheets of sandpaper and pressing down on them, this is kind of what I refer to as micro bending, where you got very small scale imperfections or pressure points on the fiber. This could have happened during manufacturing. It may have happened when you're processing the fiber, both in like coloring or tubing. A lot of this can be reversible, assuming we didn't have a problem to begin with. And if we do have a problem, we may have created that during the manufacturing process. This will give you a graph of the dB loss in power. dB is, of course, a logarithmic scale. It's really the power to which you have to raise 10 to get 100. We'll say it's 2, 1,000 is 3. And you can kind of see that 3 dB in this case is 50% loss. What they call the divorce law. If you lose that much power, or lose that much, you're going to be divorced. Excuse me. The impact, of course, on the loss is that, you know, we're not going to have enough signal at the other end in order to pick that up with the detector. Dispersion. This is the spreading out of the light pulse as it travels through the fiber. And to a large degree, this limits our bandwidth for a fiber, because as these pulses spread, they remove the gaps between the two pulses. And when it gets to the other end, it looks like one pulse over several pulses, and it creates errors, what we call bit errors. The types we're going to be talking about are modal dispersion, chromatic dispersion, and polarization mode dispersion. Modal dispersion, and this slide shows a couple different types of dispersion. The bottom part shows really the modal dispersion, where you have different rays, and if we're looking at this fiber, we're seeing that it's a step index multi-mode fiber. In other words, we're seeing more than one mode go down the optical fiber, and we're seeing that these rays are traveling different paths going down the length of the fiber. So as these rays travel these different paths, which are different lengths, why they're going to arrive at different times on the other end. In the colored, the upper part of the graph, you'll see that a light pulse consists of many different wavelengths. And these wavelengths, which we call colors, travel down the fiber at different speeds or different velocities. A red and a blue and a green in this case will travel at different speeds going down the fiber. It's just part of the electromagnetic wave. And it arrives at the other end at different times. And that's another source of dispersion. But in step index multi-mode fiber, it's really the modal dispersion which is going to cause you the biggest problems. In single mode, it's chromatic dispersion. We only have one mode of light going down the center of the fiber. So it's chromatic dispersion, which is the biggest problem. And even though the laser wavelengths are very narrow, they still consist of a few wavelengths of light. And again, those wavelengths travel down the optical fiber at different speeds. And as you can see on the other end, arrive at different times, and the pulse spreads, causing errors, bit errors in the detectors. Polarization mode dispersion. I think I'd rather label this slide, are we ready for 100 gigabytes per second? Because this one, which is fairly new, I think it was discovered in the 90s, what it's saying is that each electromagnetic wave consists of two orthogonal waves, electrical and magnetic, and they can travel. If everything was perfect, these two waves or these two modes would travel down the optical fiber at exactly the same rate. But a fiber is not perfect. It has geometric issues. It has elliptical cores. It has stresses on it. It's not perfect, both in terms of geometry and in terms of stresses on the fiber. And as these modes travel down the fiber, they come across, or they see different indexes of refraction as it moves down the fiber. And where that comes from, primarily, is that when the preform was made, and it was sintered, or it was heated up more in order to consolidate it, and it becomes then this clear glass you see as it cools down. What happens during that cooling process is it makes molecular changes within the structural changes within the optical fiber, and those changes are going to affect the index of refraction, which is the speed of light over the medium. So as these two modes travel down the fiber, you can see that some of them are going to get delayed. Some of them are going to be fine. Now, if the fiber produced was perfectly geometrically perfect, and all the stresses outside the fiber are equally or symmetrical, then you wouldn't have this issue. But we know that fiber does get stressed. It sees vibration in the wind, vibration from trains or whatever else is going by. The fiber is not perfectly centered, or constant. It's not concentric. The core cladding may be a little bit off center. The core itself may be a little bit elliptical. All these things are going to affect polarization mode dispersion. And this is not a huge thing at 1 gigabits or less, or up to 2.5 maybe. But as we get into the 10s and the 100 gigabits, we're going to find that some of the latent systems that are in place may have a problem with those data rates, because at those speeds, these pulses are going to be so close together. I mean, just think about the speeds at which we're talking about. 100 gigabytes per second. I mean, that's incredible. And now, so any kind of dispersion is going to affect its ability to reach those goals. So I think we're going to find, as we move forward into these higher bitrate systems, we're going to have to go through and test a lot of these systems and find out how much this polarization mode dispersion exists, and then reevaluate what we're going to do at that point. So I think this is going to be important in the future. And dispersion. Well, here's what we've been talking about. We've got an impulse pulse. You know, the laser flipped on and the laser come on and went off, or the LED came on and went off, and we got this pulse separated in time from the following pulse. And what we're trying to do on the other end is we're trying to recognize whether that was a 1 or a 0 when it gets down there. Well, we're going to have a certain amount of dispersion, and we know we can't get rid of that. So in the low gigabyte systems, why we can space these pulses out far enough where we can compensate for that, where the other end they can see the differences in the pulses. They can see the zeros, or when you get a gap. If we have too much pulse broadening, too much dispersion, when we get to the other end, then we're going to have a lot of bit errors, and we're going to have a lost information, and we're not going to be able to decipher what we put on that optical fiber. Attenuation. As we discussed earlier, attenuation, some of that is built into the fiber, and we can't do anything about that. We just have to buy the best fiber we can for the application that we're going to use it at. And then we're going to have to process that fiber such that we're going to induce the least amount of attenuation on the fiber. This is where the cabler comes in, and his ability to put that fiber in a cable and keep it unstressed, or put that fiber in a position of least stress, is going to have that fiber relaxed and able to have these millions or billions of light pulses over the optical fiber without losing a lot of light. A typical maximum value for single mode fiber right now, and these values primarily come from Corning, but I think the other manufacturers are very similar. For single mode, it's going to be 0.35 dB per kilometer. That's the way we measure attenuation. At 1310, which is just outside the water peak that I showed you earlier on that one slide, and 0.25 dB at 1550. And the reason we like 1550 for transmission is we have the lowest amount of attenuation in the electromagnetic spectrum at that wavelength. Typically, after cabling, we're going to see actually a reduction in this attenuation, because the values that we're getting from Corning they're accurate, but they're also on a spool. They're wrapped up fairly tight on a spool. So they may exhibit additional information, or they're padding it a little bit, knowing full well that it's going to be unwound and put into a cable. And most of the time, our values after cabling are about 0.34 at 1310 and 0.2 at 1550. For multi-mode fiber, it's very similar. We don't have a lot of data ourselves on multi-mode fiber, but generally speaking, we're looking at roughly the same issue. We're going to have a 3.3 at 850 and a 1.2, 1.3, 1.4 at 1310 or 1300. I'm sorry. I hope that was clear as mud. Okay, dispersion. Dispersion, as we discussed, is the spreading of signal pulses. It's overwhelmingly from the fiber manufacturer. Okay, you've seen that from the Rayleigh scattering and the fact that different pulses or different wavelengths travel down the optical fiber at different velocities. We get those values from the optical fiber manufacturer. He gives us what the dispersion is at different wavelengths, or at different wavelengths. He also tells us what the numerical aperture was, and if you look back, you can calculate then your acceptance cone from the numerical aperture to give you an idea of what the light acceptance or the acceptance cone is for that optical fiber. Dispersion, except for the polarization mode dispersion, is not very affected by the manufacturing process. If it is, then you may have a problem with your cable manufacturer. It's very difficult for us to put those kinds of problems in a fiber. We're going to talk about a couple of advanced fiber types. Where there's a lot of, there's not a lot. There's some specialty fibers that have been created over the years for certain applications. You know, there was a fiber created for radiation environments. There's fibers created for the military and defense industry. What we're going to talk here about a couple fibers for the telecommunications industry. When they developed the dense wave division multiplexing to put on a single mode or an optical fiber, they found that they had a problem with what we call 4-wave mixing at 1550, which is the bandwidth or the wavelength that most of this fiber is used for long distance communications. So what they had to do is they had to correct that lower dispersion at 1550 and move it back towards 1300. That created a bigger dispersion, more dispersion at 1550. But what they found was that increased dispersion reduced the amount of 4-wave mixing. And what 4-wave mixing is when these light waves, we'll say there's several light wavelengths together. These lasers, can fire there's several lasers that can fire into this optical fiber at the same time in different wavelengths. What they found is that when we'll say 3 wavelengths, as they move down the optical fiber, they would interfere with each other and create a 4th wave, and which would cause errors in the communication system. So they designed this fiber specifically to overcome those issues. The next fiber is what we call the cutoff shifted or cutoff shifted single mode fiber. It's the lowest loss fiber at 1550 that Corning or maybe anybody else makes. It was originally used for transatlantic applications where a submarine cable through the under the oceans, and it allows for the highest data rates and the longest distances between repeaters. They're going to start offering this more and more to telecommunications companies, and not just primarily for submarine cables, so we can have the higher data rates that everybody is trying to get. Our insatiable need for data is incredible. I remember taking an optical fiber to a bunch of independent telephone companies when I was younger. I mean, when I first started, and we would show them a pair of optical fibers, in this case, a 6-fiber cable. We talked to the communications people about the capacity of the fiber and what it could do for them, and they just kind of say, well, why would you ever need more than two? You know, a operating fiber and a backup fiber, and so because they couldn't imagine, you know, the use or the demand that information was going to be in the future. Then we started seeing over a very short period of time an exponential requirement for optical fibers. We're making now optical fiber cables in the hundreds in certain applications. So as people demand more and more bandwidth into their homes and their businesses, this is going to be a continuing growth business. The government is supporting it through funding for co-ops and residential areas where they couldn't afford to put ultra high rate systems in their areas. So they want everybody in America to be able to utilize the bandwidth necessary for the education, for their entertainment, or whatever they're going to use it for. So I think it's been an exciting 40 years for me, and I see that this continuing. You know, they may come up with a new medium someday. I'm sure they will, but it's amazing how much they've utilized optical fiber and its capacity to meet the demands for the future. Here's to give you a relative size of the optical fiber. You can see the fiber on the left and the fiberglass from a ceiling tile and then a human hair. So we're talking about, you know, a very small diameter, medium, and it's incredible. I keep saying it over and over again, but it's incredible the amount of information that we can move down that fiber. And that's the end of my presentation. I know I'm a couple minutes early. If you'd like to ask any questions, or if you had any issues with what I was talking about, please let me know. Let's see.
Okay, this is Mike Riddle again.
Yep.
Thanks, Dan. And this is the Q&A portion of today's presentation. And for all of the participants, we've decided we're going to do something new. That is, whoever asks the best question, we're going to send you a genuine in-cab t-shirt. And the judgment will be the staff and management of In-Cab America, and our decision will be final. So best question gets an In-Cab t-shirt.
Well, thanks for listening to me, and I know I wasn't the smoothest presentation you ever heard, but hopefully I did get the information across that will help you better understand the technology.
Okay, we had one question via chat where somebody was asking about the G654 fiber, and wasn't it initiated in the early 90s and specifically deployed in Japan? And yeah, that's true. It's newer in the sense that it's being used in different ways now because the latest generation of it supports both the longer distances with the ultra low loss and the dense wave division multiplexing. So we're seeing it used to be used predominantly, like almost exclusively, for submarine applications for transoceanic cables. And but now we're seeing it used in terrestrial applications too. And in fact, the use of the non-zero dispersion shifted fiber is declining. And there's some expectation that the G654 fiber will take its place. Okay. And Dan, do you see the other question that's now come up through Q&A?
Let's see, I'm trying to find a mic.
Click on Q&A, and the question is, how much does temperature affect the index of refraction?
I'm not aware that it does affect the index of refraction.
Yeah, that's my understanding too.
It's simply a measurement of density. You know, I guess if somebody went to the trouble of trying to do an experiment, I'm sure this is a mathematical calculation, you know, that's been around for, I mean, if you look in textbooks, you're going to see a lot of different materials with an index of refraction ratio. Water, for instance, is 1.33, glass is 1.5, air is 1.00029. There's several published indexes of refraction, and but I haven't read anywhere where heat affects that. I mean, other than the fact that heat affects it as the glass cooled down and solidified, it does affect index of refraction in terms of in terms of density variations within the optical fiber, but I don't know how you would ever determine what those were.
Yes, I see Justin has also replied, the index of refraction only changes due to density and over the normal operating temperature range of optical fiber. You would not expect a significant change in density. I'm sure if you carry it out to 6 or 7 decimal places, maybe there's a change, but for all practical purposes, it doesn't affect. And if you look on the optical fiber manufacturer's data sheets, you'll find just one value of the index of refraction for each wavelength. So they don't say plus or minus or give you a temperature coefficient to adjust it. You just get one value. So for practical purposes, it doesn't change. And then Dan, I don't know if you see it, but Chuck Gill, forgive me, I hope I pronounced your name correctly.
Special equipment for termination on the faster fiber.
Yes.
The only thing I would say on a single mode high capacity system is you're probably going to have to use fusion splicing, and the latest and greatest connectors on one end of it as it plugs into your equipment. Beyond that, it's just a question of buying good cable, splicing it up with the lowest amount of loss and the best splicer you can get, and terminating it properly with professional mechanical connector installers. So I think that's the most you can do to enhance that installation.
Hey, good. Do we have other questions?
Do you see plastics playing a bigger role in the future of optical fiber versus silica-based glass? Kurt, I do not. You know, what I see in the future, unless plastic has a specific application, you know, like for cars, I mean, automotive, or, you know, tanks or inside ships or something. But for telecommunications, I don't see them plastic being a viable option for the high bit rates.
I'll add to that plastic fiber is something, I hate to say it this way, but it's like it won't go away. I first heard about it in the 90s, and it was supposedly going to be the wave of the future. And it just hasn't panned out because the actual optical performance is vastly inferior to that of the silica glass used in conventional optic cables. The latest that I heard about this was some years ago, and the thought that plastic fiber might be better suited to fiber to the home type applications, to be cheap for that last little connection to get to somebody's house. But there too, I've not seen in reality that really, you know, getting any traction in the marketplace. And
quite honestly, we see almost the opposite. We see people at residences wanting a glass fiber to meet their bandwidth requirements for streaming video and other communications requirements. The other thing we're seeing as a result of the COVID is a number of people now are going to be working from the home, requiring more and more information. So I think plastic fiber, you know, it's, you know, obviously it's easier to terminate. It's probably cheaper, but it certainly doesn't have the growth capability that a glass fiber does.
Yeah, and I see some discussion about temperature sensing and applications. And some, for utilities, you can use conventional single mode fiber for temperature sensing. And there are other applications where you might want to use the multi-mode fiber, typically the 50 micron multi-mode fiber that Dan mentioned at the beginning. But you can do basic temperature sensing and even acoustic sensing with conventional single mode fiber. Now, there are special applications, especially in the oil and gas industry, where they have special fibers for measuring very high temperatures. So at the bottom of an oil well, I don't remember what it is, but it's very hot. And, you know, because think about it, you're getting close to magma, which was the basis of lava. So the temperatures go way up. And in those cases, they're extremely specialized fibers where the coating will include gold, I think, or something else to kind of reflect the heat and protect the cladding in the core of the fiber. But like I say, those are very special and kind of outside the, you know, the scope of what we were planning to talk about today. And then there's the question, when will the cutoff shifted fiber start being offered? Dan, you want to field that, or you want?
Well, to the best of my knowledge, it's offered right now. I've got a message from Corning here that they've changed the trademark. It's no longer TXF, it's TM. But unless I'm wrong, Mike, you'll have to answer this. As far as I know, it's available right now.
No, you're absolutely right. Corning has their product. I thought it was the TXF that you just mentioned, but yeah, it's available right now. And the latest version of it that's, as I say, getting some traction as a replacement for non-zero dispersion shifted, or, I mean, Corning might, that's my layman's take on it. Corning could be more definitive as to what's going on or how they see it being used. As I say, that's my layman's interpretation of it. But the point is, it's G654E, and it is available now. Okay, other questions?
Is G653 completely abandoned by all? Some designers like it for Raman applications. That'd be for sensing, right, Mike?
Yes.
I can't answer. I'm not an expert in sensing applications. That's up to you, Mike, or whoever.
I'm like you. I have a layman's understanding of sensing applications, maybe more than that, more than the average person, but I can't consider myself an expert. I don't know anything about that particular fiber type. There is a question from Carlos Gandia. So if we had opportunities, you would recommend the use of G654 fiber against non-zero dispersion shifted fiber? And my answer to that is, I don't know. I'd have to look at the cost and compare the performance and look at what you're trying to achieve in your application. And I would bring in Corning and get their input on it before I would make that decision. I have to say, I don't have enough information at that point, but we would certainly be glad to help somebody explore that. Anything to add, Dan?
No. That's exactly the way I would handle it too.
Okay, any other questions? Okay, well, I think we're 12:10 is what my clock shows, so we've covered our hour and a little bit more with questions. And, oh, wait, thanks. Well, oh yeah, okay. Appreciate everybody's time and attention today, and my thanks to Dan for covering this presentation. And there will be more. You guys, people had given us some suggestions for other topics, so please keep an eye out for future topics. And then please remember that if you want to get Professional Development Hour credit, you will look for an email from us, which will give you a link about where to go to take your test. And I made it really hard this time, really hard. So you're really going to have to think about it.
And if you didn't like my presentation, please contact mike.riddle@incabamerica.com, and please tell him everything that you hated about the presenter. Thank you.
Oh no, now my inbox is going to blow up. To build on Dan's point, also in that email will be a link for a course evaluation. So please do give us feedback, the good, the bad, and the ugly, as one might say. And
I promise
also,
to get better.
You've got ideas, if you got ideas for future topics you'd like for us to cover, don't be shy about putting those in there as well. So thanks everybody, and we are finished for today. Bye-bye.
Bye.